In this video, we will introduce the concept of spontaneous processes. Spontaneous in chemistry does not mean immediate or automatic. We will also be covering the concept of entropy, which along with the concept of enthalpy is a major part of the study of thermodynamics. One important concept to keep in mind is what the word spontaneous means in chemistry. Spontaneous means that a process is thermodynamically favored. So what does that mean? All this means is that a process will happen eventually without any continuous outside force. It does not mean that it will go fast or it will happen instantly, although it could go fast. Usually, spontaneous just means that a chemical reaction will happen eventually. Let me give you an example. Carbon can exist in a number of forms. Graphite that is in pencil lead can be converted to diamond, but it takes a lot of pressure and high temperatures to make this happen. So this is a continuous outside force that is needed to make this reaction happen, and this reaction is not spontaneous. So let's consider the reaction happening the opposite way, diamond converting to graphite. I know most of you have seen diamonds and have never seen them converting to graphite, but is this a spontaneous process? When a reaction changes direction, it also changes spontaneity. So if the reverse reaction, graphite to diamond, is non-spontaneous, then the diamond to graphite reaction is spontaneous. But we have never seen this happen. This is because spontaneous for a chemist means it will eventually happen. Diamond will eventually turn to graphite, but it might take millions of years. Another example of spontaneous reactions is gasoline combustion. Gasoline is a mixture of many different hydrocarbons, but the main hydrocarbon is octane, C8H18. Combustion happens when oxygen and a spark, which is provided by the spark plugs in your car, mix with the octane. The products of this reaction are carbon dioxide and water. For this spontaneous reaction, we will also need a spark of heat or energy for the reaction to proceed. Isn't this an outside force? It is, but it is not a continuous outside force. The opposite of this chemical process, carbon dioxide and water forming octane and oxygen, is non-spontaneous and will not occur on its own. So the final definition we have of spontaneous in chemistry is a reaction that once initiated will continue on its own, although it could take a long time to complete. View this video of dominoes falling. Is this a spontaneous process? Entropy is a major part of the study of thermodynamics because isolated processes that have an increase in entropy are spontaneous. What is entropy? Entropy, which is represented by a capital S, is a measure of how dispersed the energy of a reaction is in a thermodynamic system. Let's say, for example, we have a cold pack. A cold pack is a mixture of ammonium nitrate and water that are separated until the pack is activated. A cold pack is used to treat strains and sprains that cause tissue inflammation because cold reduces inflammation. When the ammonium nitrate and water are mixed, the ammonium nitrate breaks into its ions and the water surrounds those ions. Therefore, the ammonium nitrate becomes more dispersed from its solid form to its aqueous form, and the entropy increases. The second law of thermodynamics states that the entropy of an isolated system always increases with a spontaneous process. Sometimes entropy will decrease, and sometimes entropy will decrease in a spontaneous process. In these cases, the system is not isolated, as is the case with DNA forming a double helix from random base pairs. You might be asking yourself, second law of thermodynamics, what happened to the first law of thermodynamics? The first law of thermodynamics is the conservation of energy law. It states that energy is neither created nor destroyed. The second law of thermodynamics pertains to the direction of natural processes. For example, heat always flows spontaneously from hotter to colder bodies, and never the reverse, unless external work is performed on the system, or the entropy of an isolated system always increases. And there is a third law of thermodynamics as well, but we will talk about that one later. The system is what is being studied. If you are boiling water, the system is just the water, and the surroundings are everything else around the system. For our boiling water example, the surroundings are the pot, the oven, and even you. We define the universe by saying that it is a system plus the surroundings. An isolated system cannot exchange heat or matter with the surroundings. Essentially, a thermos is an isolated system. A closed system cannot exchange matter, but it can exchange energy with its surroundings. An example of this is a closed soda can, because you can put the can in the refrigerator and it will get cold, transfer of energy. An open system can exchange matter and energy with its surroundings. An open soda can is an example of an open system. Entropy is sometimes defined using a statistical model of energy dispersion. To illustrate how it works, have you ever played with dominoes? Dominoes have two sides with a number of dots on one face of small plastic tiles. If you were playing with dominoes and I told you to put down these 5 dominoes, you could do it like you were playing the game of dominoes and do it one of these 2 ways. Or you could do it a lot of other different ways as well. You could stack them one on top of another, or you could align them so they could fall, or you could just put them in a pile. There are probably endless different ways to put these dominoes, but only 2 ways that involve the sides matching up. So, statistically, it is more probable to find the dominoes mixed up. Now, if we relate these dominoes to gas particles, statistically, it is more probable to find the gas molecules mixed up than to find them ordered. Now think about this situation using large numbers of dominoes or gas particles, and we come to the following 2 conclusions. 1. Substances that are mixable with each other will mix spontaneously because there is a higher probability of a mixed distribution. 2. The most probable mixing pattern produces a uniform distribution of particles throughout the volume they occupy. To connect this statistical view of entropy to thermodynamic systems, we will rely on the work of Ludwig Boltzmann. He was an Austrian scientist and a philosopher who developed an explanation of how atom properties related to the physical properties of matter. He proposed that the entropy of a system is related to the total number of ways that particles could be arranged. The number of different arrangements of these particles is defined by the variable W. Then Boltzmann linked the number of probable arrangements to entropy with this equation. Entropy equals a constant, called the Boltzmann constant, times the natural log of this W variable. The probable number of arrangements of the molecules in the system at a given temperature are the number of accessible microstates. A microstate is a specific configuration of a system where the particles occupy certain positions and momentum with a statistical probability at a certain temperature. What does all this information about microstates mean? It leads us to our 3rd law of thermodynamics. Considering a gas with all the particles translating, moving through space, rotating, and vibrating, when you cool this gas down to a liquid and then to a solid, the molecular motion decreases until it reaches 0 at 0 Kelvin. This is the definition of 0 Kelvin, where all molecular motion stops. The 3rd law states that the absolute entropy for a substance at 0 Kelvin is 0. This is where there is no more dispersal of energy and motion stops. The 3rd law also lets us calculate absolute entropies for a substance, and we define these absolute entropies as standard molar entropies. The symbol for the standard molar entropy is S degree. S is a letter used to represent entropy, and the degree symbol means that entropy is measured at standard state, which is 1 atmosphere at 298 Kelvin. You can imagine that the particles of a gas will be more dispersed than the particles of a liquid, which will be more dispersed than the molecules of a solid. This corresponds to this relationship. S solid is less than S liquid is less than S gas. This means that when the substance undergoes a phase change, its entropy also changes. Some other ways in which entropy changes are with temperature changes, volume changes, and when the number of gas particles change. When temperature and volume of a reaction increase, so does standard molar entropy. This makes sense if we think about this in terms of kinetic molecular theory. If you increase the temperature of a substance, the particles will start moving faster. When the particles are moving faster, they can be dispersed easier, which leads to a higher entropy. If you increase the volume of a reaction mixture that contains gases, the molecules will spread out, leading to more dispersion. This again leads to a higher molecular entropy. If you increase the number of gas molecules made in a reaction, or if you make gas molecules in a reaction, entropy also increases. This is because entropy increases as the dispersal of the gas particles increase. Entropy increases as the molecules get bigger because they are able to rotate and translate more. Entropy also increases as molecules get more spread out rather than more compact. This is because they will take up more room, and this will lead to a higher dispersal as well. Also, entropy is higher for molecules that are more flexible rather than molecules that are more rigid. Now we will work on some problems using the concepts discussed in this video. Identify the following processes as spontaneous or non-spontaneous and explain your choice. A. Helium gas escapes from a latex party balloon. B. A photovoltaic cell in a solar panel produces electricity. C. Water vapor condenses on the sides of a glass of iced tea. For letter A, when helium gas is escaping from a latex balloon, you need to ask yourself about the time scale this is happening on. Even though we usually do not see a helium balloon get smaller as we watch it at a party, eventually it will lose all its helium gas. Take a few balloons home from a party, and in a few days they will be on the floor, because a lot of the helium has leaked out. So if a process will eventually occur without an outside force, the process is spontaneous. For letter B, where a photovoltaic cell in a solar panel produces electricity, you need to ask yourself about the outside forces that are occurring in this process. When a photovoltaic cell is being used to produce electricity, there are outside forces occurring to make this process occur. In the case of a solar cell, it is the sun's energy that is the outside force. When the sun goes away, the photovoltaic stops working, and the panel may stop producing energy. If a reaction uses a continuous outside force, it is non-spontaneous. For letter C, when water vapor is condensing on the sides of a glass of iced tea, you need to ask yourself if this does happen at all. Will water vapor condense on the glass of cold liquid? Yes, it will, because water vapor from the surrounding air is cooling down enough around the cold liquid that it turns to a liquid itself. So yes, this is a spontaneous process. Diamond and graphite are two allotropes of carbon. On the basis of their different structure and properties, predict which has the higher standard molar entropy. Diamond and graphite are both made of carbon. Diamond has a very rigid structure, which makes it one of the hardest substances on Earth, and graphite has a more flexible structure with layers of carbon that can pass by each other. Since graphite is more flexible, it has a higher entropy because the carbon atoms can be in a lot of different positions. Rank the following compounds in order from lowest to highest standard molar entropy, S degree. A. C2H5O liquid, C2H5O gas, C2H5O solid. B. CBr4 gas, CF4 gas, CCl4 gas. C. NH3 gas at 300 degrees Kelvin, NH3 gas at 400 degrees Kelvin. D. CO2 solid, CO2 gas, CS2 gas. E. The structure of hexane and the structure of 2,3-dimethylbutane, which are both gases. F. 1 mole of CH4 gas in a 1-liter container, 1 mole of CH4 gas in a 2-liter container. G. NaCl solid, NaCl aqueous. For letter A, which asks about ethanol as a liquid, ethanol as a gas, and ethanol as a solid, we need to think about states of matter. Which state of matter will have the lowest standard molar entropy and which will have the highest? We have talked a lot about gases in this video because gases have the most freedom to move around, the most dispersal of energy, and therefore the highest entropy. If gases have the most freedom and the highest entropy, then liquids must come next because they can flow past each other. The lowest standard molar entropy goes to solids because they are stuck in place and cannot move. The order of these molecules is C2H5O solid is less than C2H5O liquid is less than C2H5O gas. For letter B, we have 3 gases already, CBr4, CF4, and CCl4. So the order of entropy is not going to be determined by states of matter. But these molecules do have differing molar masses. Remember, entropy increases as the molecules get bigger because they are able to rotate and translate more. On the periodic table, bromine has an atomic mass of 79.90, fluorine has an atomic mass of 18.99, and chlorine has an atomic mass of 35.45. All of these molecules have 4 of these different atoms and 1 carbon. So therefore, the order of these molecules is CF4 gas is less than CCl4 gas is less than CBr4 gas. For letter C, we have the same gas again, NH3, at 2 different temperatures. The order of entropy is not going to be determined by states of matter, but rather by temperature. When temperature of a reaction increases, so does standard molar entropy. This is because the particles will start moving faster and they can be dispersed easier, which leads to a higher entropy. So the order of these molecules from lowest to highest standard molar entropy is NH3 gas at 300 degrees Kelvin is less than NH3 gas at 400 degrees Kelvin. For letter D, we have different gases and different states of matter. First of all, the gases CO2 gas and CS2 gas will have higher standard molar entropy than the solid CO2. So the compound with the lowest standard molar entropy will be CO2 solid. Then, to decide between the 2 gases, remember entropy increases as the molecules get bigger because they are able to rotate and translate more. On the periodic table, oxygen has an atomic mass of 15.99, and sulfur has an atomic mass of 32.07. So out of these two, CS2 gas has a higher molar mass and a higher standard molar entropy. Therefore, the order of these molecules is CO2 solid is less than CO2 gas is less than CS2 gas. For letter E, we have 2 different structures of molecules, although they do contain the same number of carbons and hydrogens. Pause the video now to count the number of carbons and hydrogens in both of these molecules. Entropy increases as molecules get more spread out, rather than more compact. This is because spread out molecules will take up more room, and this will lead to higher dispersal as well. So the hexane molecule will have the higher entropy, and it will be higher than the 2,3-dimethylbutane. For letter F, we have the same gas in different volume containers. The order of entropy is not going to be determined by the states of matter, but rather by volume. When the volume of the container that gas is in increases, so does the standard molar entropy. If you increase the volume of a reaction mixture that contains gases, the molecules will spread out, leading to more dispersion. So the order of these molecules is CH4 gas in 1 liter is less than CH4 gas in 2 liters. For letter G, we have the same substance, just in different states of matter, but now we do not have a gas, so we can assign this to the highest entropy. We now have solid and an aqueous solution. This is a scenario we did not talk about much, but it should make sense that as we dissolve a solid in water, we increase the amount of ways the solid could arrange itself. This is why aqueous solutions have higher standard molar entropy values than their solid counterparts. The order of these substances, from lowest to highest standard molar entropy values, is NaCl solid is less than NaCl aqueous.